So before we actually go through talking about balancing reactions, let's talk about the different types of nuclear decay pathways so that when I say a decay product, you know what I'm talking about. Now, there's only a handful of actual decay pathways, and we're going to go through the symbols and we're going to try to keep them up here on the left to give you an idea what they look like and also how to represent them. Now, first one we're going to talk about is an alpha particle. Now, all an alpha particle is a helium atom with 2 electrons missing. So this is a helium plus 2 atom. Ejecting a helium atom off a nucleus gets rid of 2 protons and 2 neutrons at the same time. So what this is going to have the effect of doing is effectively lowering the mass of the parent atom. So when we have our decay pathway, our decay product is going to be an atom with a weight 4 less, 2 protons less, and 2 neutrons less. Now, we can also have decay products relating to what are the principal components of an atom. So one other pathway is electron injection. This is a beta decay. And in beta decay, what happens is that a neutron decomposes into a proton and electron. The electron is ejected out of the nucleus and goes out to space. And what we're doing when we do a beta decay is that we're increasing the number of protons in the nucleus but keeping the mass the same. So we want to do this if we had an excess of neutrons in the nucleus. Another decay pathway is the neutron ejection. So let's say we have decayed and now we've gotten to a point where we have way too many neutrons, but we don't really want to eject something like a helium nucleus. Well, what we can do then is that we can eject a neutron. This is going to be represented with an N superscript 0. And all neutron emission does is change the proton to neutron ratio as well as lower the weight of the nucleus. Now the third principal particle here is going to be a proton emission. Now when we do proton emission, what we have are too many protons relative to our neutrons. And so this is going to be represented by a P+. And when we have P+ ejection, this basically lowers the number of protons and increases the neutron to proton ratio. So those are the three fundamental particles. Let's talk about an anti-electron, a positron. So what a nucleus can also do is it can eject an anti-electron or a positron, and this is represented by a beta+. Now, what a positron is an electron with a positive charge, and what the effect of this positron emission is that it converts a proton to a neutron by getting rid of its positive charge. So effectively, a positron is very low weight, and it takes the positive charge off the proton and gives us back the neutron. Now the big reason we want to do this is like when we have proton emission, we talked about how we have too many protons. When we do positron emission, we don't have enough protons, and so we're going to convert our neutrons to protons. Now our last decay pathway is going to be gamma emission. Now gamma is kind of a weird one. You see it written a lot and it doesn't make sense because the gamma emission doesn't really change the number of protons or neutrons in the nucleus. Well, it's a bit more complicated what's going on. Typically when we have a decay pathway, when we eject an alpha particle or a beta particle or a positron or a proton or a neutron, we finish up with what's called an excited state. So if you go back to Chem 1 and you look at what an excited state is, an excited state is when you have electrons filling orbitals and they're not all filling the lowest possible orbital. So there's a lower energy orbital that's unfilled and a higher energy orbital that is filled. This is what happens when you have a decay pathway, is that sometimes when they finish, the protons and neutrons have their own orbitals within the nucleus, and when we finish, they're actually in orbitals that are higher in energy than they could be. So what will happen is that the protons and neutrons will decay. They'll release light to get them to lower energy orbitals within the nucleus. And this is gamma decay. So what we see when we see gamma decay is no change in mass, but we do see a release of energy. And what we typically see when we see this release of energy is a change in the spin. So electrons have a spin of 1/2, protons have a spin of 1/2, and neutrons have a spin of 1/2. Now in the nucleus, this can be added. So if we have something like hydrogen with 1 proton, so it's spin 1/2. If we have deuterium, proton plus neutron, that's a spin of 1. If we have tritium, proton plus neutron gives a spin of 1.5. What we'll see with gamma emission is actually the spin number will change. So they'll start pairing up their spins like they do when we have excited states decay for electrons. And when they start pairing up their spins, we see a decay to a lower spin number. So these are your different decay pathways. And now that you're armed with that, go to the next video where we'll talk about how you actually balance a nuclear reaction when you have a decay product and a decay pathway.